Okay, lecture 11, equilibrium constant, part 2 of 2. So let's look at the first problem here. Determine the Kc for the reaction that is the sum of the following two reactions. So let's first add them up, as we would for a Hess's law problem. I'm going to leave off the phases, and I'm not going to cancel anything. You can see that there's some things that will cancel, but I'm just going to leave them in to help us see what's going on here. So this is reaction 3, and what they want us to find is K3. What is that in this case? The numerical value. So K1 is 0.788, but I'm going to write out the expression. And then I'm going to write out the expression for K2, the second equation. So they're all just Kc's, but when we have if we have to distinguish between two Kc's, we label them differently. That's why they're K1 and K2. So nothing new there. It's just if there's only one equation, we just call them Kc. But now K3 is, let me write it all out here. Oops, that's not a 2. Sorry, and then this is H. So I'm just using this reaction 3, so we have that. Oh, that is a 2, sorry. I was looking at the wrong one. Okay. So I'm trying to look at this. Let me put a box around it so I don't miss it here. CLF squared, CL2, CH4. So that's your K3. Now we know that these are related, and we can see that if we were to multiply the K1 and K2 together, it would equal K3. So you can see that we have CLF2. If we multiply these terms together, then on top we'd have CLF2, H2 squared, CCl2F2, and then on the bottom we have these. So when we add up equations, then the k's from the equations we added together, if we multiply those k's together, we get the k value for the sum. So if you're given two equations, or 3 or more, whatever you take, you sum up the equations, the new equation will have a k value as well, and that k will be equal to the product of all the k's from the other equations. So since we know what it is now, it's K1 times K2, we have numbers involved here, so just like that. So I did it the long way and came up with the answer, but for this next one we won't have to do all of this work. If you're given this on the exam, if I can get a hold of it here, you're given this on the exam. So determine Kc for the reaction that is the sum of the following two reactions. There's no reason to put a line out here, write the whole thing down. You can if you want, but really, when we get done, we're going to have some equation in K3 that we don't know. But we know that K3 is going to be equal to K1 times K2, and if we're given numbers, then we can find its value. And this is 18. So you can see that much easier. Now, if I might say on the exam, show me the final equation, show me the general form for Kc for that equation, but normally this is supposed to be a very quick problem for the exam. That's all. And as I said, if we have a K7 where we're adding up 6 equations, then it's going to be K1 times K2 times K3 times K4 times K5 times K6. So these would be 1K for every single equation that was part of the sum. And it can just go from there, as many as you want to add in. Okay. Now we have this guy here, 3. Determine the Kp expression for each reaction. Now, Kp involves partial pressures rather than concentrations. For Kc, that's concentrations Kp is still an equilibrium constant, but it is for partial pressures. And the reason we have these different ones is because concentrations are easy enough to work with when you're dealing with solutions. But when you're dealing with gases, it's harder to measure the concentration of a gas. It's very easy to measure the pressure. If you do any work with either high pressure or low pressure, you realize that there are actual huge catalogs of pressure gauges. So finding pressures is very easy. So if we're dealing with gases, we can put it into this form. P for pressure, and then lowercase or subscript for the pressure, partial pressure of that species. So this is the partial pressure for HF squared over the partial pressure of fluorine times the partial pressure of hydrogen. And we can put a little product sign there. And so that's Kp. We can still, for this reaction, we can certainly do this. We can certainly make it Kc and determine concentrations. They're not necessarily equal. Kp and Kc don't necessarily have the same value. They can, but they don't have to. All right, for this one, Kp, partial pressure of PCl3 times the partial pressure of chlorine over the partial pressure of PCl5. So just remember, when you're dealing with a Kp, it's partial pressures. You don't use square brackets, you use the capital P for pressure. Kp for this expression, partial pressure of methane times partial pressure of water vapor over the partial pressure of CO times the partial pressure of hydrogen cubed. You're still raising to the powers, so this is a coefficient here, so we're raising this partial pressure of hydrogen to the third power. You don't have to put the dot in there. I put it in there just because if you don't, it gets a little jumbled up. I mean, if you know what you're looking at, you'll be fine, but it's nice to put those in there just so you can, the square brackets definitely distinguish between the different species. Here you might want to have those dots in there, just show that they're separate things. Now for this, as I said, the Kp and Kc are not necessarily the same. They're related in this way. So we have the equilibrium constant in terms of concentrations is Kc. This is for partial pressures, and they're related to R, which is 0.0821 liters atmospheres per kmol. And then the temperature has to be in terms of kelvins. And then N is the number of product, I should say, number of moles of product gases. Yeah, there's just no easy way of writing this out. You had to write out the whole thing. Minus number of moles of reactant gases. And that's the sum total of them all. So if there's two reactants, you have to add them all up. But let's take a look here. It's easier just to do this out. Fortunately, I've used up so much room here. Let me rewrite this equation. Now they're saying this, so note we have T in there, so we need to have a temperature, and they told us what it is above. They say Kc is 6.11. The temperature is 367 Kelvin. If it's in Celsius, you have to change the Kelvin. And then our Kp is equal to Kc, let me just rewrite this again, delta N. Kc is given, and that's how it's going to work. You'll be given that value. You could also be given Kp and solve for Kc, but this is usually how we go. 0.0821. I'm going to leave the units off because Kp has no units of measure, so we're going to just ignore them anyway. That gas constant is what it should be. And then T, we're just going to put 367. As long as it's in kelvins, we can now leave off those values. Now, delta N is 2. Sure. Minus the sum total of gases on this side, 1 plus 3, 4. So it's negative 2. And then we solve from there, and I came up with 0.00673. I'm going to redo it here. Yep, came up with the same thing. There you go. So it's important that you get this 2 minus 4. So it's the total number of moles of gas on the product side. Since it's just 2, nothing else is here. So it's 2. And then on this side, it's 1 mole of gas, 3 moles of gas. It's a total of 4 moles of gas. So 2 minus 4, and that will be the deal. So also, if delta N is 0, here's where I said that Kp and Kc are not necessarily the same. You can see that Kc was 6.1 and Kp is this, so they're definitely different from each other. But if delta N is 0, that would mean that the same number of there's the same number of gas molecules on both sides. So if this is 2, if this had been 2, it would be 2 minus 2 or 0. So this whole term would disappear, and then Kp would equal Kc, because it would be RT to the 0. So if you have the same number of gas molecules on each side, then Kp does equal Kc. So we have a chance for it to happen, but we have to have the right conditions. So just be careful when you're adding these up. Let's try another one here. All right, Kc, let me just write out the expression. So for my class, you'd need to know this expression, and then I'll provide all the data that goes in. Leave off the units. You can certainly put them in, but they have to be discarded anyway because Kp doesn't have any units of measure. Neither does Kc. Now we have delta N. We have 1/2. I set it up this way just to make it a little tricky. 1/2 plus 1/2, so that's 1, minus 1/2 plus 3/2, that's 2. So this comes up to be 77.8. So it's a weird reaction, but weird-looking reaction, but you have to go with the rule. You just add up. So instead of having whole numbers, they have fractions. Well, that's just how it is. Some reason, and you do have points when you're studying chemistry where it's important to have fractions as part of your reactions. Not many, but they can come up, and that is the deal. But